about optimizing database backup performance using data science techniques. Welcome, everybody. My name is Kevin Fiesel. I am a Microsoft Data Platform MVP out of Durham, North Carolina. I run a predictive analytics team, and I also have a blog called Curated SQL. The idea of Curated SQL is I try to find and link to 5 to 10 interesting posts per day in the data platform space. So that's curatedsql.com. The question for today is, how big is your backup window? And I use the term in the title, using data science techniques, but this is really a talk for database administrators because we're talking about backups. We're talking about making backups faster. And the impetus behind this is a lot of us have fairly tight backup windows and want to try to find ways to reduce how long it takes to take those backups. So we're going to use some data science techniques to resolve that question. We're going to try to minimize the amount of time that it takes to back up existing databases. Now, I'll talk you through the techniques. There's nothing particularly scary or fancy about them, but we'll see how we can use them in a practical scenario to assist with a problem. In order to assist with the problem, let's describe the problem. What are we talking about here? That is, backups and also database restores are critical for DBAs. So if you've got a fixed amount of time to take backups, you might run into some trouble because your databases grow over time. So the amount of time that it takes to back up the database as it grows, it have a 2-hour window, it might take you, and that's a problem. So the question is, what can we do to resolve this problem? And there are several. File groups are a little bit faster for queries, but also we know that we don't necessarily have to back up those file groups all the time. Now, newer editions of SQL Server, say 2017, 2019, have built-in improvements around backup performance. So simply upgrading to a newer version of SQL Server may provide some performance benefit when it comes to backing up databases. We could get rid of obsolete tables. If data is being stored and we're backing it up, obviously that takes time. If we don't need the data, if it's not useful data, by getting rid of it, we reduce the amount of time it takes to back up that database. We can use other techniques, data compression, column store indexes, etc., to reduce the data size, we reduce the backup size. And if we reduce the backup size, we reduce the time it takes to write that backup, and usually the time it takes to even process. If we split data across multiple file groups, we could take file group backups at separate times and not have to overwhelm our system all at the same time. And in a similar pattern, we could use differential backup. I have the history of the world up until now, the state of things as of right now, and then I could take differential backups to track the changes in a hopefully faster way than taking another full backup. Eventually, I'll need to take another full backup, but of eking out a smaller backup time during the week, for example, and then make up for it on the weekend with new full backups. Now I can also configure backup settings. And I'll give you a hint of all of the things I mentioned here. This is the only one I'm going to talk about today. The others are very important. They're very useful. You might find that one of those by itself solves all of your problems. But let's suppose that it doesn't. That's where we're going to dive next. So let's talk about these settings. At its statement. So we back up a database called Scratch. We back it up to disk, and I specify where it's going to be. A couple of tags, no format, and init. Basically, They're incredibly basic. There was a file there. Don't worry about its contents before, and just write something new. Write new backup headers. But there are other settings as well. The first one that I want to talk about is called block size. So block size is the physical size of blocks that are being processed. And valid values range anywhere from 512 bytes at the smallest to 64 kilobytes at the largest. And I have the entire list of valid values right here. Now, in fairness, block size matters a lot if you're backing up data to a CD-ROM. Also, in fairness, if you're backing up data to a CDRW, if you're doing that, I can give you a really great way of speeding up your backups. Not doing that. Essentially, yeah, if you're writing backups to tape, block size matters. Pick the right block size for your tapes. That will give you a performance benefit. If you're writing to disk, block size really doesn't matter. Max transfer size. This is to be transferred per single operation. So ranges from megabytes. And again, these are the entire set of enumerated values that we have available to us. So max transfer size, I like to liken it to a bucket. This is how big is your bucket. So I can pour this much water into the bucket, and then I can take that bucket and pour it out into a bigger bucket somewhere else. And so in order to fill up that bigger tub, I need to take the bucket, fill it up, bring it over. Take the bucket, fill it up, bring it over. And this size of my bucket tells me how many times I need to fill. Increasing the size of the bucket means that I can bring more with me when I pour it out later. Buffer count is a companion to max transfer size. This is the number of buckets that we have. So when I describe the example of taking a bucket, pouring it out, well, this is more like me and 20 of my closest friends, each taking a bucket, filling it up, and going and pouring them in. So all 21 of us are pouring in this. And so we could expect things are going to go a lot faster than if it was just me pouring. Buffer count is an integer. That is the only thing that stops us from defining whatever is buffer count. So there's no hard maximum. However, there is a soft maximum. And think of it as 1,024. The reason I pick that number is if you have 1,024 buffers, each of which is 4 megabytes, you are spending 4 gigabytes of RAM just to take a single backup. That 4 gigs of RAM can't be used for your buffer pool. It can't be used for servicing other queries. It can't be used for other backups going on concurrently. So even if you've got a lot of RAM, spending 4 gigs just for a backup, that's a fair amount of memory right there. Going higher than that means you're spending even more RAM. And it can limit your capability to take several backups concurrently. Finally, file count. File count, again, is an integer. And this tells you to tell SQL Server to stripe your backup over multiple files. This gives the device that I have here. If you have direct attached storage, generally a number somewhere between 1 and 12 is going to be the best fit. That's gonna depend on what kinds of drives you have. Is it NVMe? Or a lot of details that we'd have to talk about and probably test to get the right answer on. But usually several files beats one file. And generally there's a curve where the more files you add, the better it is until you reach a point when it flattens out, and then it'll actually drop over time. If you're saving to a SAN instead of direct attached storage, usually you want to cap out at no more than about 12. So basically with direct attached storage, up to 12 files per drive which means you could write to 3 separate drives concurrently, 36 files at a time. If you're talking about a SAN, you're going to overwhelm the SAN much more quickly. So try to limit to about 12 max, because you typically won't get many gains above that when you're writing to a SAN. And the final attribute, I lied about there being 4, compression, true or false, whether or not you want to compress your backup. There's a minor CPU cost for backup compression. It is very minor. So minor as I've never actually noticed it to be significant ever, but technically it is there. But it does lead to much smaller backups. So my default is to say yes. Now, there are possible cases where backup compression may cause a problem. And in the event that backup compression is slower for you, don't use it. So again, test out your environment, your scenario, because that specifics of hardware and specifics of installation, configuration, of workload, those like any hard and fast advice I mean, even with number of files, I had to give you a pretty big range because, well, it's going to depend on a lot of circumstances that we can't really foresee. So, all right, I've come up with some new settings. So we're backing up the database scratch, and I'm writing to 2 files instead of 1. That's pretty easy. I've set max transfer size to 2 megabytes. Notice that we have to write it in bytes, not like 2 MB. Buffer count 50, block size 8K, and I've included compression. So great, problem solved. Except there's one little problem here. How do I know that those values are the best? I mean, I just picked them arbitrarily. They looked nice. So is that correct? Well, I mean, I could run that back up and then try some other values and run that back up and try some other values and see what feels right. But there's a lot of possible values. And like I mentioned, this is all going to depend on your hardware, your workload, your configuration. So even if these, they're not probably going to be the best numbers for you. So what we want to do instead of my having a number is to come up with a process that we can follow to determine what that number ought to be, or what those settings ought to be. What good backup settings look like in your environment. And in order to do this, we can test every setting. Well, there are, we do the math right here, 8 block sizes, 7 max transfer sizes, technically an infinite number of buffer counts, but let's say I have, 8 right here. And let's say that I have 7 file counts. So 8 times 8 times 7 times 7 is 3,136. If it takes you 10 minutes to back up on average, that's about 22 days straight of backups just to figure out which of these 3,136 settings is the best. That's not going to be a great use of time, especially because, well, we're coming here to try to reduce the amount of time that it takes to back up. And I just told you to take 3,100 times as long once. Not a great answer. But we do have possibility of sampling. So by sampling, what I can do is, instead of looking at all 3,136 possibilities, let's pick some combinations. And we can pick either entirely randomly, random sampling, or we could pick and choose based on educated guesses. I am going to take the easy route and random sample because I don't have any information about your environment. So I don't have educated guesses yet. So let's pick arbitrarily and see what comes out of it. The way that we can sample is using the DBA Tools PowerShell library and a little bit of very simple PowerShell to perform this sampling. So instead of taking 3,130 database backups, we take a much smaller number. And that smaller number is, closer to 50 or 100. So I am going to, while we're pulling this up, grab the PowerShell script that I did not prep in here, which is okay because I've got it. All right. Optimizing backup performance. Let me go to my GitHub repo where I've got the script readily available. And I will give you a link to this repo after the fact, so you'll have access to it. First thing we want to do is create a little function to generate a Cartesian product. Cartesian product, a cross join. This is our ability to look at all possibilities. So simple function, I grabbed it from a GitHub gist. And then I have my instance name, I have my database name, and I'm going to create a Cartesian product of my block sizes, buffer counts, max transfer sizes, and file counts. Quick reminder, I've set compression to true. I'm just defaulting to true to simplify the process. And so I take Cartesian product. There are 3,136 possible entries. I want to get about 100. So why 100? 100 is a pretty good starting point. It is, first of all, going to give you, hopefully, several cases of every one of these individual parameters. So I've got 8 and 7, which means on average, everything goes well, I would get about 4 to 5 database backups for each block size. I would get 4 to 5 for each buffer count. Hopefully I get more. Hopefully I get 10, 15. But even if we skew really heavily, I'm still going to have a decent combination, a decent number of entries. If I got perfectly average, then I would have about 12 and a half from this 8 and about 14 point something from this 7. But worst case, I still have several cases where I've got this particular block size. So we're going to get random, and it's going to range from 0 to 100, or from a 1 to 100. And I'll say, well, if random is greater than, 0 to 99. If it's greater than 96, it's going to be one of 97, 98, 99. Well, 3 out of 100 is about 3%. And this is completely random. You know, I'm not trying to bias my search to have certain combinations. So all I care about is, just give me 100 random entries in here. So I'll get approximately 100. I may get 102. I may get 98. Not a big deal between those. And what I'm going to do is run backup DBA database right out to from the SQL instance, and it's going to write to disk the database. It'll be a copy only backup. So this is full backups, copy only with compression, setting my buffer count, file count, max transfer size, and block size. And for each one of those, I'm going to take how long it took and write that out to a text file. And I'll do that for several databases. So this probably will take a while to finish up. And ideally, you would do it in a production environment. In practice, I'd recommend, well, if you've got something close enough to production, if you've got a pre-production where you have similar hardware, where you can simulate a similar workload, this will at least give you, but it'll be close. And that's where we're going to get to with analysis. By the way, if you have any questions at all through this, please add them to the Q&A. I have it right in front of me. So if you do have questions, happy to answer them at any point. But now let's do a little analysis. We want to solve something called a regression problem. So we have data. We have actual data with actual values. And I want to build a model that says, well, if I tweaked these values, what would my result look like? There are several techniques for performing regression, and 3 of them that I'm going to talk about today. One is linear regression, one is random forests, which I'll also talk about decision trees, and a third is a neural network. So linear regression is a really simple concept. The idea is that I have some input variables: buffer count, max transfer size, block size, compression, file count, and I have some output variable, number of seconds that it takes to back up the database. I believe that there is a linear relationship between those inputs and this output, and I just want to figure out what is that linear relationship. This is the crux of linear regression. So in this chart, for example, there is a pretty strong linear relationship between GDP and purchasing power. So purchasing power parity per capita normalized, leading to higher life expectancy. There's an exception, and that was Kuwait during the 70s and 80s. There's a little afield from what we're talking about here, but in general, line here. And we're looking to see, can we find something like that in our data? For decision trees, a decision tree is really just a bunch of if-else statements. So if database size is less than 50 gigabytes, and memory usage is less than 32 megabytes, and file count is less than 10, then here's our result. So we have these if-else mechanism by which we can make predictions. Well, a decision tree is fine, but a decision tree is pretty limited in the amount of information that it can reasonably absorb and reflect without failure. So we have a technique known as a random forest. The idea of the random forest is we're going to find a bunch of these decision trees, and we're going to try different things. We may have different subsets of the certain versions of this not to have certain input data. Like you're not allowed to use buffer count in your analysis. And we try that with a bunch of different trees. And we tell them you can have this many levels, but this other tree can only have this many levels. And we have other mechanisms for how sophisticated or simple or poor the information is for each tree, bring them all together and have them vote. And we essentially take all of those results, combine them together, and give that back to the end user as the consensus answer, or the resulting answer from what all of our random forests elements have chosen. And I mentioned neural networks. Neural networks are a powerful technique for analysis, but they are fairly complex and a little bit tougher than what I want to talk about today. It is a good technique that I think will give you a very solid result, but as we'll find here, we don't always need them. So I am going to go to this notebook. So this is a notebook in Jupyter Labs, and I have a script. I have a process that shows you how to load this up in case you're not familiar with Jupyter notebooks at all. So again, I'll give you that link at the end. And I have a descriptor of most of what we just talked about for the past 20 minutes. So I'm not going to cover this over again, but instead I'm going to come down here. The language that I'm using is R. If you're not familiar with R, no big deal. This is a domain-specific language that is extremely good for statistical analysis. So let's talk about what we're doing. First thing that we're doing is loading up some libraries. Actually, okay, good. I've already got the libraries installed. So the first library is called the Tidyverse. The Tidyverse is an opinionated set of packages intended for creating clean data, creating data that we can easily analyze. The next package is Random Forest. Random Forest package allows us to create those random forests. The next package is Carrot, which is a library that is intended to help data scientists with data processing problems. And finally, EV-Tree is a package that creates what are called evolutionary trees. And as a form, we'll see that a little bit later on. I also want to note that my input data set has databases of 6 separate sizes. So I've got this one database called BAC. BAC is a real database that I worked with, and its maximum size was 136 gigabytes. And what I did was I took the biggest, meanest table from that and I just dropped it. I had my own local copy. And dropping the biggest table got me down to 89 gigs. And then I took the second biggest table and I dropped it. And I dropped the next one. Dropped a couple more. So eventually I had 4 separate versions of this database at different sizes because I believe that the amount of data in a database will make a difference in how long it takes to back up that database. Not a crazy belief. And therefore, I want to include different sizes in here. I also have 2 forms of Stack Overflow. One was a 10 gigabyte version. Another one was a 50 gigabyte version. I did not have the full Stack Overflow version, which has, I think it was like a terabyte or so of data. So didn't have that one. But this should give us a range anywhere from 10 gigabytes to about 130 gigabytes for my sample, which I think is a broad enough space to give some idea of what's going on. And what I'm going to do is set a new variable called database size. And by the way, let's talk about what we're doing in here. For each one of these databases, I'm reading a delimited file, so a CSV, comma separated values. I'm defining that I have 5 attributes here. This is what we wrote out in PowerShell: block size, buffer count, max, and duration. And I'm just defining the column types. These are all integers. So each one of these is populating what is a data frame. Think of that as a table, a result set. So I could operate off of that data frame and do things like add a new column to it, which is database size. And this rbind function is my way of adding a new column to each row in, to combine together all of the rows in each one of these. So I have all of the rows from 31 gigs, all of the ones from 58, from 89, 136, and the 2 Stack Overflows. I've just smashed them all together into one data set called backup stats. So I could next convert block size to kilobytes. So I'm going to divide it by 1024 and remove the original block size. So great. And then, so that I'm not leading you on, an early version of this talk, I led people through a bad assumption. That assumption is that max transfer size and buffer count matter. What matters is the combination of the two. Technically, what matters is the max transfer size in megabytes times the buffer count, because it's not so much about how much water hub over a given interval of time. And it doesn't matter if you have 21 people carrying a small bucket or 2 people carrying a big bucket. If you have the same amount of water going through, it's the same for SQL Server. It's the same amount of memory, and memory is the ultimate concern, not number of buffers and not max transfer size. So I created this memory usage count, and I remove buffer count and max transfer size as inputs. Also, the second bad assumption that I'm going to lay out here is number of seconds is actually not the thing that we want to predict. What we want to predict is almost a database throughput. And I mentioned that with the water filling analogy that I keep coming back to. We're actually less concerned with how many seconds does it take to fill up this tub, and more concerned about how much water can I pour into the tub every second. The reason is tub depends on how big your tub is. A tiny tub is not going to take nearly as long as a huge tub. So as a result, very size dependent. By translating this to a measure which is hopefully independent of size, I don't have to worry as much about database size. If I look strictly at duration, what I'm going to see is that the database size dominates. That is the most important thing. Essentially, the answer would be, well, make your databases smaller. If you drop all your I mean, yeah, technically, but you know, I can't just go dropping all my data in production. People get a little salty about that. So let's build out some training, some test data sets. Let's build some models, understand what we can do to analyze our data. I'm going to set a random seed so that every time I run this, I always have the same values. Then I'll pull out, basically randomly shuffle my data and pull out 70% of the data as my training data set. 30% of the data Whoops, I forgot to run this. So I have 381 test samples and 100 training samples, 160 test samples. And if I take a quick look at that data, I don't care what the database's name is. The database name doesn't matter in how fast it takes, how long it takes to back up, or how quickly it can back out is file count, duration, database size, block size, memory relate to this measure, which is seconds per gigabyte. And so let's figure that out. The first thing I'm going to try is creating a random forest. So that random forest, I want to predict duration. So remember, this is going to be a problem. I want to predict duration as a function of block size, memory usage, file count, database size. And we'll generate that model. And then I'm going to try to understand what the model tells us. So what this tells us is database size has by far this biggest percent included in mean squared error. Essentially, what the model is telling us is if you want to minimize duration, reduce database size. File count says it's very small negative. Block size, very small positive. Memory usage, tiny positive. But shrink that database, by which I mean drop all your tables and your database backups are way faster. Technically accurate, not useful. So let's take a look at the model. This explains 90% of the variance in the training data set, which is really high. I mean, if you don't think through the consequences of this model, you might say, yeah, I'm doing a great job. I explained 90% of the difference in how long it takes to back up databases. And the vast majority of that is how big the database is. So I can generate some predictions. And what we'll do is we're going to create outcomes, basically combining together my test data and those predictions. The outcomes. This is what the model model pred. This is predicted seconds per gigabyte. Yeah. So this is what the model predicted. This is what it actually took. 200 seconds, 203. That's pretty good. 123, 122. 197, 210. That's okay. This 82 and 19 obviously is bad. Now we could just go through and look at this and eyeball it and say, I think that's good, but we have a better way of doing this. And that's called root mean squared error. The root mean squared error is a measure of how far off we are in the terms of the thing we are looking at. So what this means is how many seconds on average are we off when taking predictions of these backups. And the outcome tells me this is about 26 seconds on average. And we can see our actuals range at 20 at the minimum and a couple hundred at the maximum. So if I plot this data, what am I plotting? What I'm plotting is the prediction minus duration. So ideally, what we would want to see is essentially a straight line at 0, or at least data points floating around 0. If we got that, then we'd be pretty happy. We would have a pretty good model, but we don't have that. What we do have is the small databases. We're predicting that they take a lot longer than they really take. The mid-sized databases, in general, we're doing okay. Although this data point right here, I think something must have been happening on my computer at the time, because processing was just, it was very weird. It took a lot longer than expected. But this large database, we can see this is a lot longer. This is taking a good 5 minutes when it should have taken 4.5. So 4.5 or even 4 minutes. That's a lot longer than we expected. And I can see that this is clustered. And I'm probably not spoiling it for you by saying that these clusters are roughly aligned with the database sizes. So let's try again, but this time I'm going to use that throughput measure. I'm going to use how much can I dump into the tub at a given, over an interval of 1 second. How many seconds does it take to load a gigabyte of data? Again, based off of my same inputs. So new model, I generate importance measures, and we can see actually database size still matters. It is still a very important measure, even though I have already taken into account the database size. That is how important this is. But we can now see memory usage actually matters a lot. So use means faster backups. More files, faster backups. Although adding one file doesn't give you as much of a benefit as adding more memory. Block size is essentially 0. There's no real benefit in writing to disk, specifically to NVMe, by setting different block sizes. That really, again, only matters if you're writing to tape drives, to CDRWs, to situations where you have to this model scores overall. And variance explained is only 62%. You could look at that and say, ooh, that's a lot lower. But what I want to caution you against is looking at that number of variance explained and saying, well, higher is always better. Because this is variance explained of throughput, not of duration. And to show you what the results look like, let's generate predictions. Let's combine the test data with the predictions and show you some outcomes. So remember that the first example, it was 82 seconds. Well, we predict 20 instead of 19. So way better. 199 versus 203, 127, 202. Again, you can eyeball this and say, yeah, these look pretty good, but how good are they? Let's look at root mean squared error. We are on average 10 seconds off. So instead of being 26 seconds off on average, we're at 10 seconds off. That's a pretty big difference, or 10.75, so 11 seconds off. And if I plot this, what I want to see again is ideally, I want to see that straight line or those dots bouncing around 0. And what I have is dots that are bouncing pretty close to 0, except for a couple of weird exceptions. Again, there was probably something going on, maybe some system process that was happening while I was running these backups. For the most part, though, this is pretty close. Despite having a lower variance explained, the interpretation of the model is this is much better as a model than what I had before. But I can also test the boundaries. I can also see what exactly can I expect from this data set. And so I'll put in different buffer counts. So I've got everything from 1 up to about, what is that, 8.1 million? Sorry, 81 million buffers. And everything else stays the same. So this is memory usage. So we could assume that it's basically I'm adding more buffers and I'm keeping the max transfer size the same. And what do we get? As memory usage increases, number of seconds to take the backup looks like it decreases. There's a small increase, but whatever. Decrease. And then it seems like after 4095 or so, it just stays the same. What is the reasoning behind this? Well, first, we see a decrease over time, or over memory size. So as memory goes up, the amount of time that it takes to take a backup decreases. This makes sense. This is going back to our analogy. We're adding more people who can hold bigger buckets and pouring faster. Therefore, our throughput is better. But why does it cap off at 4 gigs? The reason for that is specific to decision trees. A decision tree, remember, is the if-else statements. Well, there's a limited amount of nuance that we can have with a decision tree, and that is entirely limited to what are the inputs of my data. I had as the highest possible amount of memory used 4 gigs, 4096 megabytes. Anything above 4096 megabytes, Random Forest doesn't know how to guess that answer. So what it does is it just says anything 4 gigs or higher, you're going over here in the 53-second bucket. So what I'm getting at is you're going to want to limit your analysis if you're using Random Forest to the range of where you sampled. Don't try to leave the sampling area because the answers you get may not be correct. Let me compare this to what really happened in the data set. And here are different examples of where I had 4 files, 31 gigs as the size. And again, I don't really care about block size because we noticed that it doesn't make a difference. So when I hold database size and the file count fixed, I had these in my sample. And we can see that the number of seconds does in fact go down as memory goes up. So it's 66 seconds with 30 megs of memory. It drops down to about 56 here, 58 to 56 in this range. So we could find a sweet spot. We don't necessarily need the most memory. We could say, well, 128 megs gives us about 57 seconds. 55 to 57 versus 51 for 256 megs. Maybe it's worth having 256, or maybe we're okay with 128 and shaving off 5 seconds instead of 10. And so I've got a little bit other analysis on here, and we can see what this looks like as I change the database size. We can see that there is not a flat line, which is what I ideally wanted to see in terms of throughput seconds per gigabyte and database size. There is still an effect. And I guess the moral of the story is, database size matters a whole lot. So what I'm now going to talk about is evolutionary trees and a little bit of genetic algorithms. Genetic algorithms are a topic that I really like, but I am one of the, I could say, of people who really enjoy genetic algorithms. For the most part, genetic algorithms were supplanted by support vector machines and neural networks. It's rare that you'll find people using genetic algorithms in. I love the idea, but a totally different talk and a blog series. So if you're really interested in learning more about it, I do actually have a lot of content on the topic. But it's more from a, I don't know, let's have fun perspective than you're going to want to use this in your environment perspective. Evolutionary tree actually might be more interesting. So an evolutionary tree, think of this as a way of trying to build up random a tree, not necessarily a random forest where I arbitrarily select and I arbitrarily redefine the parameters. Let's try to build a tree and find the best tree that fits our data. So this is one tree instead of a whole bunch of them. The benefit to doing this is we get a single tree that we can interpret using the plot function. And if I look at this plot function, what it tells me is the most important thing we look at is database size. And it says if you're less than 50 gigs, look at memory usage. If you're less than 32 megs, look at file count. If you're less than 10, then we're probably going to have a throughput on average of, well, let's call that 2.15 or so. But there's a pretty high variance. If you have more than 10 files, you're in this range. So we can see that certain combinations of attributes actually lead to more seconds per gigabyte. Gigabyte is actually bad. We want fewer seconds per gigabyte. So this right here is probably our worst. Big database, more than 50 gigs, and less than 30 megs of RAM. It's going to take you the most time. So what we want to do is try to find maybe the lowest. And this looks like you've got a small database and you've got more than 32 megs of RAM. Small database, lots of RAM, backups faster. Now, that interpretation, that visual interpretation, fine for this size, but really what this tells us is we're not actually going to be able to control database size effectively. I'm taking database size as given. You have a database which is 2 terabytes, not let's shrink that database to 1 terabyte and try. If you can't, well, we take it as given. So let's say this is a 2 terabyte database. Well, now we can say, okay, if memory usage is less and our database size is less than 57, the seconds per gigabyte. So that's my 2.3. If I have more than 30 megs of RAM, well, I'm not there. I actually have a database that's bigger than that. So if my database size is bigger, it's 2.2 seconds. If I use more than 120 megs of RAM, it's only 2.0 seconds per gigabyte. So what this is telling me, a couple of things. Thing number one, I want to use at least 120 megabytes of RAM. Thing number two, the corollary to this, there is apparently a sharp cutoff after about 120 megabytes, given my data sets, given my environment. It seems that adding more RAM did not provide a sufficient enough boost to merit a separate branch in the tree. It turns out that I could probably cap my database, individual database backups somewhere around 120 megabytes and be fine. So that might be 120 buffers of 1 megabyte max transfer size, or 30 buffers of 4 megabyte max transfer size. I could increase it a little bit, but I don't need to give it 4 gigs of RAM because it's not going to be hugely more effective at 4 gigs of RAM. So that's what, and I can look at small databases and see that, well, memory is still. Does matter a little bit, especially when memory amount is small, that it seems that file count has some positive effect. Random forest, the file count benefit is smaller than the memory benefit. Once you've peaked on memory, then we could be looking at files. And apparently in my case, when writing to that one direct attached NVMe, so even though these say greater than or equal to, you can treat them as this is the threshold. This is the optimized point. I don't need to go further because I get a small gain, but I don't want to go below that because I'll get a loss. So I could look at 10 files. I could look at 120 megs of RAM for big databases, 32 megs of RAM for small databases, and start to think about writing a backup script that checks the size of the database based on that threshold, based on that cutoff. Let's back it up separately, back it up a different way. And if you're using Minion backup, you can definitely do that. If you're using Ola Hallengren's script, you can definitely do this. If you've written your own backup process, you can definitely do it. If you're using maintenance plans or something like that, you can't do this, but you could switch to something that does do it. Database backup time is a critical factor for you, then it will allow you to control for it. I can build out my predictions, I can append them to the test data, and I can see my results again. So I can see duration, predicted duration, and say, these are pretty close. I mean, there's some cases where they're wrong. But again, let's look at root mean squared error. 11. We went from 10.75 to 11.29. Grand scheme of things, it's not a big difference. It's less than 1%. So around close. And if I plot this, you can see that I'm around 0, but what we also see is there's this straight line. This straight line effect actually tells me I'm missing something. There is some missing variable that is not represented by the evolutionary tree. And I could speculate. I get the feeling that this is based on not incorporating file count as much as it should, that it's really optimizing for a parsimonious model. It's optimizing for a smaller model with fewer decision points. And so I think that by incorporating file counts in here, we might get better. If-else statements. If database size is less than 50, use 32 megs of memory. If database size is greater than 50, use 120 megs of memory. Like if I just do that, I get a model that looks like this. It's pretty close. So what do we do next? Well, I could take my process and basically, actually, I just talked about this. I could take that random forest, and the random forest tells me predictions. But we wanted to reverse the process by finding out which parameters maximize performance. That's where the evolutionary tree came into play. So deploy my model someplace, maybe use SQL Server machine learning services, maybe use my own standalone R or Python installations, test the result, retrain the model. If you buy new hardware, you want to retrain. If you are looking to buy hardware, like, hey, we want to upgrade our SAN and we're trying out 3 competitors. Which one of these would be best for databases? We can run a process like this, sample our database times, and see what is better. So over the course of today's talk, we covered a data science scenario from I have a problem to here's my implementation. Optimizing backups. Hopefully, one of the things you got out of this, if you're a database administrator, is that data science can matter to you as well. There are, in this case, several algorithms that we could try. We did show 2, random forest and evolutionary tree. To fill you in on some of the stuff that's not in here, linear regression was pretty close. It wasn't quite as good as the random forest version, but it was close. And we could try other techniques as well and probably find something that's even better. But we saw how that compared. And we saw the analysis portion takes seconds to run. The database backups takes a long time. And that is probably the most painful thing, getting that initial data. But one thing to remember is you have some initial data already. You're taking backups every day, hopefully. So if you know what your settings are today, you can start collecting that info. And you know what? Instead of taking 100 backups in one day, just bam, 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 one after the other, take it over the course of a couple of months. Switch around the settings each time and see what the changes look like. And what you'll end up with is a set of randomized data that you're able to process here. So that's one way of getting this data in a production scenario without overwhelming your systems. And if you want to learn more, if you want to get slides, if you want to get links to additional resources, if you want to get the code that we used today, check that out, csmore.info/on/backups. If you have any questions at all, please do feel free to reach out to me. My email address, my Twitter handle, right here on the slides. With that, if there are any questions, let's get them in Q&A. And otherwise, hope you have a wonderful weekend. And I think there's